Welcome to Washington, D.C. I'm James Foster, the co-director of the Institute for International Economic Policy, or IIEP as we call it, here in the Elliott School of International Affairs at the George Washington University. Thank you all for being here with us today for a conversation with Sir David Hendry and Dr. Jennifer Castle, taking stock of climate change, earth, air, fire, and water. Professor Hendry is no stranger to GW, having joined us here in Washington on many occasions, often with our marvelous forecasting and macro group, including Tara Sinclair, Fred Utes, and Neil Erickson. Welcome back, Professor. And to Jennifer, thank you for being here from one of my favorite places on earth, Magdalen College, where I spent a Trinity term a few years back. Welcome to DC. This is the third in our Rethinking Capitalism and Democracy series, and is being co-sponsored by the Thunderbird of Global Management at Arizona State University as part of its series on finance and sustainability. I'd like to thank co-organizers, Dr. Ann Florini of Thunderbird and Dr. Sunil Sharma of the Elliott School for putting together such an amazing panel today. Sunil sends his regrets as he is on his way to India due to a death in the family. Now, in just a moment, I'll invite Ann to the stage to introduce the series and our distinguished guests. But first, just a few words about the Elliott School and our institute. As the largest school of international affairs, the top-ranked Elliott School has a remarkable location, a quick stroll from the World Bank, the Treasury, the Fed, and the Fund. IIEP is a research institute within the Elliott School where scholars and policymakers present and discuss the newest findings on such topics as global governance, climate change, and multidimensional poverty. Our China Conference series recently featured David M. Lampton of Johns Hopkins discussing the state of U.S.-China relations. Last week's Envisioning India series brought together Vijay Kelkar and Ajay Shah to diagnose India's recent slowdown in economic activity. And on Monday, our Multidimensional Poverty series brought Sabina Alkire from Oxford to DC for a discussion of global trends in the global MPI. The last episode of this series featured Simon Zodick speaking on sustainability and global finance, while the next episode will feature Alex Barkari on February 24th and Art Wilmarth on March 24th. If you miss an IIEP event, check out our YouTube channel on IIEP GW. I now welcome to the podium Ann Florini, co-organizer of today's event. Ann is clinical professor at the Thunderbird School of Global Management, Arizona State University, where she directs programs at the Washington, D.C. campus. Have a look at her recent article with Sunil in Finance and Development entitled Reckoning with Systemic Hazards. Ann will moderate today's session and will start us off with a few introductory comments. Ann.
James, thank you very much, and welcome to everyone for what I think is going to be quite an intensive and important session today as part of our series. My name is Ann Florini. As James said, I am at the Thunderbird School of Global Management, and I would like to thank James and GW for co-sponsoring this series of events with us to quite an extraordinary audience talking about quite extraordinarily important topics. I want to start by introducing our two guests today and then just take a moment to explain why it is that we have asked them to speak to you, why what they are doing is so important, and what it means for policy and for the private sector. The main presentation will be done by Sir David Hendry, who is co-director of climate econometrics and a fellow at Nuffield College at Oxford. He has been professor of economics at Oxford and of econometrics at LSE. He has held visiting appointments at a wide range of major universities, University of California at Berkeley, San Diego, Duke, Yale, and as well as being Leverhulme Personal Research Professor and ESRC Professorial Research Fellow at the University of Oxford, where he chaired the Economics Department from 2001 to 2007. The list of honors is quite long. I will not go through them all. Sir David was knighted in 2009. He is past president and currently honorary vice president of the Royal Economic Society, a fellow of the British Academy, the Royal Society of Edinburgh, Econometric Society, etc. I think it is very clear that David is one of the world's leading econometricians, and it is a true pleasure to have him with us today. Dr. Jenny Castle is an official fellow in economics at Magdalen College, Oxford, and an associate member of climate econometrics at Oxford University. She previously held a British Academy postdoctoral research fellowship at Nuffield College. Her research interests lie in the fields of model selection and forecasting, and has published 2 books with David and a monograph on climate econometrics and overview, as well as more than 30 articles. David will do the main presentation today, and Jenny will be speaking to some of the modeling issues involved in their very important work. Before I turn it over to them, I want to do a little bit of framing. This is the 3rd in our joint webinar series as part of the GW series on capitalism and democracy, and the Thunderbird series on finance and sustainability. But it's actually our 4th joint event. The first was based on the article that Sunil Sharma and I wrote on reckoning with systemic hazards that James mentioned. And that was done back in June. We started with a focus on looking at this overarching complex system that we are all part of, the human, economic, and political systems, and the natural system. All 3 spheres are now interacting in some very dangerous ways. We have to stop thinking of environmental issues as an externality and understand that we are endogenously driving systems. How do we manage this? How do we govern this? How do we understand this? That led to the 2 seminar series that are now underway, and many of the events are joint. Today, we are very honored to have Sir David and Dr. Castle, because it is really vital to have both rigorous data analysis and clear communication of how compelling that analysis is of where we stand. Knowing what data matter takes a very sophisticated judgment informed by a deep reading of the wide array of relevant scientific disciplines. Knowing how to analyze and model takes extremely advanced econometric skills and insights and development of new techniques. Understanding how data and models translate into policy and action proposals that can help us avoid catastrophic climate change and tipping points takes wisdom. Communicating all of this clearly and concisely takes, well, someone like Sir David. There will be a lot of very vital material in this presentation. I am happy to say that they have agreed to share the slides afterwards. So when the presentation is posted, so will the slides. So for now, I recommend that you follow the route map that is embedded throughout the presentation and prepare your questions. Please post those only in the Q&A. The chat may not be monitored. We look very eagerly forward to this presentation. And with that, Sir David, let me turn it over to you.
Right, so thanks very much for your kind introductions, and I hope that we can pitch this at a level that both explains what we do, why we do it, and what conclusions we draw from doing it. Most of you might be a bit baffled by the earth, air, fire, and water underneath, which of course Aristotle misunderstood, but it dates back about 700 BC. And it's very important that we understand all the ingredients of what's causing climate change, and those 4 are fundamental to it. So, as a summary, for those of you who are only going to stay the first 5 minutes, crucial lessons from past mass extinctions of life on Earth tell us we need to worry. We've got information from many sciences on the causes and consequences of both climate change and mass extinctions, because climate change is the main culprit. Change is the key word. It has led to past mass extinctions over the past 500 million years, and humanity is just the latest trigger. All the previous ones did not involve us. We were not around. The current one does. So we look at approaches and evidence from many disciplines and find it compelling. Increasing levels of atmospheric greenhouse gases lead to worldwide temperatures rising slowly on a very varying trend. It's not steady, it varies a lot. The ancient framework takes in 4 essential ingredients for life. We can't live without earth because we would have no food, without air because we couldn't breathe, without fire because we'd be frozen solid, and without water or we'd die of thirst. So we need them all. We have to be careful that adaptation to climate change is not meaningful if food, water, and land resources become inadequate. On the other hand, the first mitigation steps can be beneficial even against current conditions. Now, we have an econometric modeling toolkit that we've applied in many applications, and the aim of it is to get robust empirical evidence. So it's essential to account for all the things that are going on, all the changes, all the turbulent periods, all the major shifts that have occurred, as well as the relevant drivers like greenhouse gases that we know will cause temperatures to rise. We've confirmed that the trend in atmospheric CO2 is anthropogenic. That was already known by climate scientists because of the different isotopes of CO2 in the atmosphere. We've shown that future climate will be very different than paleoclimate from anthropogenic emissions, sufficiently different that it might trigger a mass extinction. We've detected the impacts of volcanic eruptions and global temperature, which is important both to see what the temperature would have been if we hadn't had all the big drops that volcanic eruptions cause, but also I'll use it as a method to explain how we do what we do and how well it works. I'll then model UK CO2 emissions over the last 160 years and evaluate the impacts of UK policy, which occurred despite major shifts like 2 world wars, general strikes, and huge shifts in technology over the period. We've shown that improved forecast accuracy of hurricanes helps mitigate their damages, and we've estimated what the costs of temperature changes of 1.5 degrees will be versus 2, and they're quite large. So the first issue to address is, can humanity really change the climate? And the answer is yes, and we'll look at that. Then we'll look at the distant past, then the last 800,000 years, then the Middle Ages, then the Industrial Revolution, come to the present, go into the future, and then draw some conclusions. What on earth can we do about what we have done? So our planet's climate depends on the energy balance between the sun's incoming radiation and the Earth's re-radiation back into space. Atmospheric greenhouse gases like water vapor and carbon dioxide are crucial in retaining some of that heat. Too depleted and the planet cools. You might not know it, but once upon a time it was a snowball with glaciation in Death Valley, recently getting the record for the hottest place on the planet. Whereas excessive greenhouse gases lead to very warm periods. So past climate change has obviously been driven by natural forces, plate tectonics, volcanism, orbital variations, and other things like changes in phytoplankton. Life has obviously survived great changes because it's still around, and it's thrived in very different global temperatures, but en route, huge numbers of species went extinct. It sometimes up to 90% disappeared because of climate change. It's not the climate. We've had very cold climates and life has survived. We've had very hot climates and life has survived. But it's the change that causes huge numbers of species to go extinct. And currently we are changing it at an astonishingly rapid rate. So here are the changes in Ice Age atmospheric CO2 over the last 800,000 years. Each point here is 1,000 years, so there's 800 points in the graph. Now, parts per million is how climatologists measure the amount of CO2 in the atmosphere. And the changes in this graph go between roughly minus 20 parts per million as CO2 gets absorbed by the oceans, and 25 parts per million as it gets given off by volcanoes and again the oceans. Now, 1 part per million is 7,800 billion kilograms of CO2. And this is what it now looks like in terms of changes. Just imagine the enormous volume of CO2 we have pumped out in just 250 years, all the others being what happened over 1,000 years. We've clearly blown the budget very fast and rather dangerously. So let's look at our four ingredients. Earth. I see that as a placeholder for our planet's land, as both the living space we inhabit and the soil for agriculture, forests, and other wild areas. The continents and their topography have obviously been shaped by plate tectonics and volcanoes, and both affect climate directly as well as indirectly, and have played key roles in mass extinctions. Currently, food supply for the Earth's population takes up roughly 40% of the planet's land area. Now, climate change has been going on for about 100 years and has increased very dramatically in the past 20 years. It increases land flooding. There's rivers in the sky that can hold more water than the Mississippi River. Just imagine when it drops that, and Britain has suffered massive flooding in the last few years from rivers in the sky being blown across after hurricanes have worn out their energy in the Atlantic. But it's also causing massive droughts and longer droughts, leading to loss of crops, massive dust storms, wildfires from Australia, Amazon, California to Siberia, the latter being a potential tipping point from tundra melting, as I'll address shortly. Crops grown using artificial fertilizer and farmland created by deforestation, plus animal husbandry, are all leading to increased CO2 emissions. And sea level rises is causing coastal flooding, which reduces the usable land area in some parts of the world very dramatically. The rivers in the sky in the top left, you can see them here. The amount of water up there, as I say, can be equivalent to those in a major river like the Mississippi, and then it gets dropped and it causes massive flooding. Alternatively, changes in climate drive rainfall in different directions. We get massive dust storms. We also get massive wildfires because of drought and a lot of coastal flooding. It's going on. What about air? Our atmosphere is a thin blue line round the planet. It's no thicker than a sheet of paper around a soccer ball. That's it, folks. That's our climate, atmosphere driven. That's all we've got. Can we destroy that? Of course we can destroy it. Currently, it's 78% nitrogen, about 21% oxygen, water vapor is about 0.4%, and all the rest, carbon dioxide, nitrous oxide, methane, ozone, and noble gases fill up the rest. How can so little of these things cause so much damage? Well, we'll see that very shortly. Earth's gravity and magnetic field are also essential to retain the atmosphere against the solar wind and protect the ozone layer from damaging radiation. We already know that our refrigerants, CFCs, HCFCs, have done enormous damage to the ozone layer in a very short period of time. Small amounts of what humanity puts up can do a lot of damage in a very thin atmosphere like we have on Earth. The atmospheric gases have also changed greatly over deep time, particularly from volcanism and the exchange of CO2 for oxygen through photosynthesis that desperately cooled the planet. That's probably where the snowball Earth came from. Atmospheric blankets certainly essential to life, but greenhouse gases receive then radiate energy at different wavelengths between the ultraviolet and the infrared. It's much easier for the radiation to get in, but on the way back out again, it gets stopped. Now, an American lady, Eunice Foote, in 1856 showed that a flask of CO2 heated greatly in the sun, whereas those of water vapor and dry air did not. We've known for a long time what climate change is due to. It's due to CO2 because it heats greatly in the sun and then it re-radiates at the infrared frequency. And that's what's responsible for much of the atmospheric greenhouse effect. And looking at our neighborhood planets, Mars and Venus, suggests that atmospheric protection needs to be just right. Earth's range has included snowball, ice ages, and tropical conditions, but it's the change from one to the other that we have to worry about. Other anthropogenic greenhouse gas emissions are also very important. Nitrous oxide. Every time you drive your car for a couple of miles, your catalytic converter is not warm enough and it pumps out nitrous oxide. And we've also got nitrogen and phosphate fertilizers, and the total nitrous oxide emissions have doubled in the last 50 years, and now about 7% of greenhouse gas emissions. N2O, which is nitrous oxide, is 300 times more potent per molecule than CO2 as a greenhouse gas. So pumping out twice as much of it as in the past is not good for solving our problems. Atmospheric methane is now double the levels over the past 800,000 years. It's about 20 times as powerful as CO2 as a greenhouse gas. There's a half-life in the atmosphere of somewhere between 15 and 50 years, depending on where it is and how it gets converted to CO2, which is then also going to do some damage. Worryingly, current estimates of methane in hydrates in the ocean are over 6 trillion tons, which is roughly twice the CO2 in all fossil fuels, even if we were to burn a lot. So methane isn't going to be a solution. Melting Siberia's permafrost would lead to a marked increase in global temperatures by a vast amount of methane emissions. Go to any lake in northern Siberia, hold a flame over a hole drilled in ice, but jump back quickly as the methane catches fire, as in this slightly faded picture. It can lead to possible collapse in rainforest ecology because of changes in rainfall patterns worldwide. What about fire? Well, I see that as a placeholder for energy rather than just fire. Presently, it's mainly from burning fossil fuels, which release greenhouse gases, and we cannot continue to consume within the carbon budget if we're going to get to net zero. Otherwise, we face dangerous changes. But there is hopes from renewable energy drawing in fire, i.e. sunlight and possibly nuclear, and air from wind. So these are flask measurements from Mauna Loa, and they fairly accurately measure the amount of CO2 in the atmosphere. And these are in levels. The previous graph I showed was in changes. And that's what the Ice Age CO2 looks like. It goes up and down over time. And this is what it now looks like. Here it didn't go above 300 parts per million over 800,000 years. Here it's going well over 400 parts per million in roughly 60 years. What about water? Well, Earth is a blue sphere, and the oceans may look vast. And David Attenborough's programs talk about the huge oceans and the blue Earth, etc. But actually, all the water on this planet is not much more than a big puddle. That's it, folks. If we take all the water in the oceans, all in all the ice sheets, all in all the rivers, lakes, and glaciers, that's it. It's a sphere 860 miles in diameter. Can we heat that? You bet. Can we pollute it? We are doing. Can we fill it with plastic waste? Can we turn it to weak carbonic acid? Humanity can do all of those things with the greatest of ease because there is so little of it. And it's one reason it rises, the sea level rises so much as temperature changes, because there's just not very much when it's spread around all over the place. Now that's all the fresh water on the planet. And if you can see it, that is all the fresh drinking water in the planet. It's a sphere 15 miles in diameter. That's all we've got. We better not waste it. So that's it. Very little atmosphere, very little water. We're boiling the planet, mainly at the poles at the moment because of the climate patterns drive a lot of the heat from the tropics up to the poles. Their temperatures are rising very fast. So mass extinctions are a worry. What about the last 800,000 years of ice ages? Get on to that momentarily. Let's look again at these fossil record disappearances, because that's how we measure mass extinctions. There's quite a few of them before 500 million years ago. And then the well-known ones are the end Ordovician, end Devonian, end Permian, the great epochs. And this graph shows the percent of species vanishing from the fossil record, which reveals the fragility of life forms to major climate changes. In fact, this one is now known to be another mass extinction. If you integrate over this, you lose something like 90% of all species that existed previous to this huge set of extinction. The first at the end of the Ordovician was from global cooling. The second also from global cooling because plant life spread in land, reduced atmospheric CO2 before photosynthesis. The third and worst near the Permian-Triassic boundary, 250 million years ago, eliminated about 80 to 90% of ocean dwellers, about 70% of plants, and it's due to prolonged volcanic eruptions in Siberian tracts. The fourth, at the end of Triassic, about 200 million years ago, that opened the ecological niche for dinosaurs, is also massive volcanism in the central Atlantic magnetic province. And then the fifth, the Cretaceous tertiary boundary, roughly 60 million years ago, when all non-bird dinosaurs went extinct. This is attributed to a massive meteorite hitting the planet. The crater is just off the Yucatan Peninsula, and it's usually implicated. But there's also a great deal of volcanism going on. The Deccan traps are pumping out 300,000 cubic kilometers of basalt. So all of these are due to climate change, cooling and heating, and not that rapidly compared to what we're currently doing. So if we now go to the last 800,000 years, ice ages were discovered by Louis Agassiz in 1840 when he visited Scotland, having seen the movements of glaciers in his native Switzerland, and he was able to explain puzzling features of the Scottish landscape, why it had the glens and mountains it did. He thought it was a great ice age, a single one, but Archibald Leakey in 1863 found plant fragments between layers of glacial deposits, so warm periods must have separated glacier. Why do I mention that? Because these are the ways we know what's going on. Dedicated people studying problems until they understand what has happened. Calculations of why ice ages occur and a timeline was drawn up by James Kroll in 1875. And he was a janitor in a school. But he showed that variations in Earth's orbit gave a theoretical explanation for why ice ages could occur, which was amplified nearly 100 years later by Milutin Milankovitch, to whom much of this is still attributed as Milankovitch cycles, who calculated solar radiation at different latitudes from the interacting changes of Earth, eccentricity of its orbit, the obliquity, the tilt of the planet, and the precession of the Earth, which side of the Earth faces the sun in winter and which side faces it in summer, because that matters. Because Milankovitch showed that what caused ice ages to start are low summer maxima. There's not enough heat to melt the ice. It snows over winter, there's more of it. There's not enough heat the next year, there's more of it. And eventually Manhattan is under 4 miles of ice. So these three main interacting orbital changes are still operating. They're ongoing. They take a lot of time relative to human beings' life cycles, 100,000-year periodicity. But the Earth has a non-circular orbit because of the gravitational influences of other solar system planets. It tilts, its obliquity has a variation of about 41,000 years, and the tilt is relative to ecliptic. And if the North always faced the sun, there would no ice. If it never faced the sun, it would always have ice. So the obliquity does matter, and it causes the seasons. And the precession determines whether the northern hemisphere faces the sun in winter or summer. And currently it's in winter, the closest to the sun. And that means we have milder winters and milder summers than the southern hemisphere. Now, our data are measured at 1,000-year intervals. It's been a huge international effort. And the graphs that I'll show you are dated from 800,000 years ago to the present. So this is what we know about the eccentricity. That's absolutely certain what it looked like from what we know about Newton's gravitational effects around the planet. And as you can see, it's varied a great deal locally, but also 2 very long cycles, a very quiescent period here, here, and where we took over the planet. It's been very quiescent. And that's quite important. Being almost circular into the future, it's quite circular at the moment. Obliquity has varied a great deal. It's increased and then it's decreased again. Precession looks as though it's always the same, but if you look at this, you can see it's very close together, whereas if you look here, it's quite far apart. So precession is varying. And this is a summertime insolation of the kind that Milankovitch calculated. So here's the data. There's a huge international collaboration in Antarctica, drilling into the ice to see what it was, how much CO2 it had, what temperatures were, and what you can deduce sea levels would be. So ice has varied a lot, CO2 has varied a lot, temperatures varied a lot, but you might also notice what we call non-stationarity. It's not varied the same way. If you were to draw lines here and here, you'd see that the later ones are much more volatile quite systematically than the others. There's been a big shift in the behavior of the temperature. And it's reflected a bit in ice. You can see it goes down much lower here than it ever did back here. And also in CO2, the peaks are above what they were. If you're going to model these things, you've got to take account of these sorts of shifts. There's an enormously close relationship between ice age variables. I've calculated the negative of ice so that it's positively correlated with everything else to make the graphs easier to interpret. And you can see they're very, very highly correlated, but they're not perfect. There are periods of quite big departures in all of them, if you look at them, least in temperature and the negative of ice, although there are some, and surprisingly big ones in the negative ice and sea level, although you would expect that when ice melts, you get sea level rises, but sometimes it gets trapped and then breaks out from the lakes that were formed and causes a massive flow quite suddenly. Now, if ice ages are really due to orbital variations, as Kroll and Milankovitch argue, why should CO2 levels correlate so closely with the negative of ice? Or it's positive, it correlates negatively. Is that what changes temperature and so ice? Well, the explanation is that the oceans hold about 60 times more CO2 than the atmosphere. That's one large amount. The deep oceans, especially the Southern Ocean, act as carbon sinks during cold periods, but release CO2 as the planet warms. It's like leaving a glass of sparkling mineral water standing out or lose all its CO2. And these enhance cooling and warming. So orbital variations drive temperature, which changes ice volume, and therefore CO2 levels that feed back to change temperature. But this is what you might call a vicious circle. As the temperature rises, it releases more CO2. As CO2 rises, it raises the temperature. You have to be very careful when you have positive feedback loops of this kind. So Jenny and I modeled ice, CO2, and temperature jointly as functions of the orbital variables for data up to 100,000 years ago. And then we forecast forward. I know forecast is a funny word to use for something that happened 100,000 plus years ago, but it's not part of the data used in the modeling. It's outside. It's sometimes called pseudo forecasts. So this is what we find. 100 steps ahead forecast. There's no data after this line. This is all calculating by simulating the model. And as you can see for ice, it does pretty well up to 40,000 years, moderately well up to 20,000 years ago, and then whoosh, the data go way differently from the forecasts of the model. And that's also true of CO2. You can see ellipses where they now lie outside the confidence bands, or the forecast intervals, as I prefer to call them, from the model, whereas all the other ones lay well within sight. Temperature is just within, but you can see it's got the same pattern. Something happened in modern times from about 15 to 20,000 years ago. Now, Riedemann has argued that humanity began to influence climate 10,000 years ago by domesticating animals and starting farming. A relatively recent paper by Stir and a large number of co-authors provide evidence of the origins of cultivation long before Neolithic farming, using what they call proto-weeds, plants that need ground disturbance to grow in new areas. And they show that this was occurring from about 23,000 years ago, which pretty much matches where things start to go wrong for our model. Now we know the Earth's orbital path into the distant future, so we can actually calculate scenarios for atmospheric CO2 in alternative futures. No human intervention, so we extend the forecast you've just seen for another 100,000 years, no more information coming in. Or continued anthropogenic emissions, keeping CO2 at 400 parts per million, approximately where we are now, or 560 parts per million, which is roughly RCP 8.5. And I start the forecast 10,000 years ago so that they're not contaminated by the big changes that have occurred recently. And this is what we see with no human impact. So this is re-estimating the model up to 10,000 years ago and then forecasting from it. And it suggests there will be future ice ages. They're well within the interval forecasts, which pretty much match the range that we've seen historically. But that's what's been happening with ice. These ellipses show you the data up to the present time. And similarly with CO2, way outside what the model says would have happened without humanity, and the same with temperature, fluctuating around. Remember, this is Antarctic temperature, which is why it's all negative. It's not the global temperature, but there are rules for deducing the global temperature from what's happening at the poles. So here's what 400 parts per million would look like relative to the last 400,000 years. That's just to focus on the next 100,000. And then 560 parts per million, hugely different. Now, Arrhenius showed that, in fact, the temperature response to CO2 is logarithmic rather than linear, and our simulations allow for that. So when we go into the future, using 400 parts per million, 560 parts per million, this is what we see for ice, this is what we see for temperature. We get a near ice-free planet at 560 parts per million, and we kind of boil it. It'll be at least 6 degrees higher than presently, which is probably going to create wet bulb, dangerous temperatures in a large part of the planet. Now, the other feature over the ice age, the last ice age, is how much sea level has risen, about 120 meters. And that's because the flatness of the oceans means that when you melt the ice, you raise the ocean level dramatically. And that's a warning for what might happen to sea level as we go into the future. So, why am I going to discuss volcanic eruptions? Well, it's because I can explain how our methods work. The dendrochronologists have calculated the Earth's temperature from tree ring growth. Narrow tree rings suggests a cold period, broad tree rings suggest the trees grew a lot in that year, and therefore a warmer, wetter period. But there are these big, what we call outliers, big spikes down. Are they volcanic eruptions? Are they mismeasurements, or is something going on? So this is the tree ring reconstruction data, and this is the current observed temperature, which you can also see is way outside what we've seen over the last 1,200 years. So we can then correct tree ring-based temperature records. We can detect the impact of volcanoes. And that's important because we can then get a volcano-free average temperature for the planet, which would be a bit warmer than it is actually experienced because volcanoes lower the Earth's temperature, and warn us that we're already having some warming relative to what we had historically. We can also distinguish temperature reductions due to eruptions from natural and human-induced variation. And this is work with research with Felix Bettis, Leah Schneider, and Jason Snowden, published a couple of years ago. Now, how do we do it? Well, eruptions create outliers in the temperature reconstruction, as we've seen, but they do so by emissions blocking solar radiation, which reduces temperatures, and we get closer tree rings. But emissions gradually get removed from the atmosphere by rainfall. And the shape of that response is relatively standard. So here's a number of recent volcanoes. I'm going to focus on the two big ones, El Chicon and Pinatubo. And as you can see, the volcano erupts and the temperature immediately drops. It puts a vast amount of material into the atmosphere, blocks sunlight, and the temperature drops. So this is solar radiation transmitted, and there's a drop of about 25% in the amount of solar radiation getting through. Pinatubo, the same thing, it drops very sharply. Now what we assume is that we can pick up the sharp drop by our methods, and then we assume it's a half of what's left, a half of what's left of that, a half of what's left of that, to get back to the basic temperature. So we create what we call a nu shape, the Greek letter nu. The temperature drops, then it curls up, it drops, it curls up. And then we put in one of these new indicators for every observation. That is, we're going to have roughly 800 observations. We've got roughly 800 indicators, plus some other things to pick up the dynamics of climate change. But we use a machine learning program that we've developed, it's called Econometrics, which puts in big blocks of these, and it only picks up ones where there really is an outlier. And then it tells you, something happened. So we can look at what happened, and these are what we call detected volcanoes. These are all the things from this top graph that have happened. You won't have heard of some of them, like Somalis that killed about 50,000 people in Britain in the period 1258 to 1260 from collapse of harvests and starvation. Kuwait, what happened then? Constantinople fell. The 100 Years' War ended. I wonder if that was due to it. And what about recent ones? Laki, which Gilbert White in his famous book on what was the start of, if you like, natural history. Laki killed by being warmer rather than colder in many ways. It brought in lots of fall gases. Tambora, most people have heard of Tambora. 1816, the end of the Napoleonic Wars. Not a good year to have a massive volcanic eruption. The year without a summer. It snowed in New Haven in July 1816. New Haven, July, snow. It's when Frankenstein was written, because Mary Shelley was trapped in a chateau in Switzerland. And of course, it's the source of J.M. Turner's wonderful sunsets in his famous paintings. And Krakatoa is another one that people have heard of. So why do we do this? Well, here's an example eruption, the 1641 Parker eruption in the Philippines. Here's the observed temperature. It drops sharply after the volcano erupts. Now we've got one of these new shaped indicators. There's one put in here, it doesn't find anything. There's one put in here, it doesn't find anything. One put in here, it doesn't find anything. Here, nothing. Here, nothing. And then here, whoomph, it says, oh, there's been a volcanic eruption. And then we forecast by taking half that distance and half of that, half of that, half of that. And that's the pattern that we have for our forecast. And that's the pattern of the data. It's not exact, but it's pretty darn good compared to what previously was a standard model used by economists as one of the best forecasting models, a first-order autoregression without a break indicator. And this class of model is a disaster in forecasting because it goes the wrong way. It wants to get back to the old equilibrium, so it thinks that the fall needs to be compensated, so it forecasts it will jump. So instead of going down, it goes up, and you get a massive forecast error and a systematic forecast error. We've published extensively in why you should never use things like this for forecasting. So that's how we do it. And then I'm going to apply this to modeling the UK's CO2 emissions. Now, we started the Industrial Revolution. In one sense, it's all our fault. In the other sense, the startling consequences are that real income levels are 7 to 10-fold higher per capita worldwide. You can look at our world in data and see these graphs of how dramatic the world has benefited. Many killer diseases are tamed, although pandemics show that we keep creating them, and longevity has roughly doubled from about 40 years on average to 80 years on average. So the Industrial Revolution led to vast benefit to humanity, but the unintended consequence was a massive increase in atmospheric CO2 and hence in the planet's temperature. So these are the annual changes in CO2 in parts per million. And sadly, despite Paris, it has continued rising. That's a worrying trend. It means that the global mean surface temperature deviations, this is the Arctic, you've seen that in the bright red in the top left picture in the route map, and this is the global temperature. The ocean heat content has been rising very dramatically, and that's also true down to 2,000 meters. And you often see graphs like this. This is the daily global CO2 reductions relative to a year earlier over 2020 from the pandemic. That's not 2012, that's 21 and then 2, just keep close together. But this is in megatons. So we get a grand total of a reduction of 20 megatons, 20 million tons. 1 part per million, you will remember, is 7,800 billion kilograms of CO2. So this is a drop in the ocean, and you won't see it here. You won't see it in annual changes, and you won't see it in the level of CO2. It looks very spectacular. It shows what can be done, but the cost of doing this by a pandemic lockdown is disastrous. This is not the way to treat climate change. We want a different solution. This is sea level rise since 1880. It's about 20 centimeters, but it's been accelerating. So we do what we call ocular econometrics. You imagine drawing a trend line through here, and look, it ends up here. So the trend has been increasing. It's been increasing even if we draw here, we end up here. So it's now 3.4 millimeters per annum versus 1.3 millimeters up until 1992. So this is a worrying trend. Sea level rise is accelerating as well. So more land will get flooded and be unusable, and a lot of infrastructure is close to the coast. Housing, hospitals, airports, trains, and so on. Now, is it us? Are we really doing this? Well, Felix Pettis and I showed quite a while back that if you calculate all the CO2 emissions due to vegetation, this is the seasonal pattern of vegetation, CO2 falls in the spring and summer in the Northern Hemisphere and rises again, so falls in the spring and summer, that's here, and then rises again in the winter as plants die back, and that's the pattern. And this is the Southern Oscillation Index, or El Nino La Nina, and that also affects the amount of CO2. This varies from -1 to just over 2. This varies from -4 to just under 1. So we're talking about 5 and 4. And this, we're talking about 340 to nearly 380, so it's 40. So human cumulated anthropogenic CO2 changes from our model are what track the growth. The seasonal pattern is due to what's happening with vegetation, and some of the departures are due to what happens with El Nino and La Nina. But the trend is us, folks. It's us to blame. So that's been an unintended cost. And we can now look to see how well has the UK done. And its CO2 emissions per capita were 12 tons per person per year as recently as the 1970s, and now they're down at 5.5. So they're below where the UK was in 1860, where it was the workshop of the world, and now at the lowest it's been in the historical record. It only goes back to 1860, and I'm sure it was lower before, but this is still coming down. The UK has greatly reduced its CO2 emissions in the last 25 to 40 years, and it's done so despite real incomes rising 7-fold. It need not be costly to eliminate CO2 emissions, and this, as we'll see, is mainly due to eliminating coal. Coal rose rapidly through the Industrial Revolution. Note that most of what was made with that coal, iron, steel, boilers, railroads, etc., was exported. So the UK was actually exporting much of its CO2. So those of you who want consumption-based CO2 measures need to remember that that would alleviate the UK of the blame for starting all of this. This is the First World War and the interwar period and the general strike, rises again, and then it's collapsed. And we'll see what was due to natural, i.e. the cost of coal type considerations, and what was due to legislation. This is oil, that's the oil crisis date, and guess what? It falls. And this is natural gas, this is its discovery, guess what? It rises, and it has been falling. I'm afraid that's the that's the renewables. What's much more encouraging is that UK CO2 emissions have fallen 92% per unit capital stock, a massive reduction in emissions and hence a huge increase in efficiency. But like I tried to explain with the Ice Age data, it's non-stationary. There's no constant correlation between anything. That's what it looks like up until the 1960s. That's then we get a rise in CO2 with the fall in coal, then we get a fall in CO2 with the fall in coal. So it can rise with CO2, it can fall with CO2, or it can do both. So what concerns us as econometricians is people make stationarity assumptions. That is, the distribution of things stay the same. And that's just not what happens in observational social science or climatology. Nothing stays the same. And the models have to allow for the fact that they're being estimated over periods where many things change. And to get a sensible model, you have to allow for all these changes. So this is the distribution of UK CO2 emissions over 40 years in roughly 5-year intervals. And we look at the next period, that's what it looks like, a dramatic increase in the period. We look at the next period, it's a dramatic increase for some of it, but it falls back for some of it. And then if you look at what's happening now, it's much reduced and it will continue to fall back. So the distribution is falling. And if the distribution is shifting, if distributions shift, you cannot rely on any of the basic theorems in your statistics training. It is not true that conditional expectations are unbiased. It is not true that they're minimum mean square error. They're rubbish. The conditional expectation here is this mean, and yet the mean next period is out here. It's completely biased. You cannot rely on conventional statistical methods to dig you out of the hole of getting proper relationships to explain what is actually going on. Our machine learning program adjusts for it. So we look at the evolving dynamic relationship between the UK CO2 emissions, its coal usage, its oil usage, its GDP, and its capital. And what we find is that GDP actually is a negative effect. and that's probably the shift from manufacturing to services. Capital is a huge positive effect, and that's despite the great increase in efficiency. And coal and oil have the coefficient you'd expect, because we know the amount of CO2 in coal, we know the amount of CO2 in oil. And that lets us build a model that we detect step shifts similar to the way we detect volcanic eruption. So for every observation, we have a step shift that ends at that observation. With 160 observations or 160 step shifts, if nothing happens because the model fits the data, the step shift is not significant and gets dropped. But if something has happened that is not explained by the model, so the model does not fit the data at that point, the step shift will be retained. We find 3 large step shifts, and they're clearly identified with major events in UK economic history. 1926 saw the Act of Parliament, which created the UK's nationwide electricity grid, hugely improving the efficiency with which electricity was used and greatly reducing the amount of CO2 emitted to get that electricity. 1969 saw the start of conversion from coal gas to natural gas. This is an oddity. Coal gas gives off CO2 when it's converted from coal to coal gas, and it's mainly hydrogen. So you'd expect getting rid of coal gas would have reduced the amount of CO2, but no, it hugely increases it because of a massive expansion in the use of natural gas compared to coal gas. So 1969 saw a big increase in the amount of CO2 given off by the UK. Not explained by coal and oil, because of course it's used natural gas. And then eventually, in 2010, following the implementation of the Climate Change Act of 2008 and the European Renewables Directive of 2009, we find a very large step that explains a big drop in the UK's CO2 emissions, conditional on its coal, oil, GDP, and capital stock. And so these are the outcomes. That's the red data. The model fit is the blue data. It has picked up a number of shifts. These are the ones I mentioned. Shifts are dated at the point that the shift ends. So a shift ending in 1925 picks up a shift that starts in 1926. Okay. Likewise, these. We don't know. If anyone knows what caused 1991, I'd love to know. That's the step shift we did find. It's not very significant, but it is picked up. But we can find nothing. It does occur in a number of countries worldwide. And that's 2010, leading to this big drop. And there's a number of outliers. 1912, there's something going on. 1926, general strike. 1945, I think everybody would know what that is. 1947 was a hugely cruel cold winter when Britain hadn't recovered from the Second World War, and so on. Now, given a model, we can produce forecasts. And I've produced 2 forecasts to show you the advantages of adopting our methods over conventional methods. These are the forecasts you would have got if you hadn't dealt with step shifts over and above what's in the model: coal, oil, excuse me, coal, oil, GDP, CO2, and capital stock. And that's uncertainty, the forecast intervals. And this is what you'd have got dealing with the step shifts. And there's the actual data. So the root mean squared forecast error is 29 for the multi-step forecast with our methods and 49 without. And we can try and examine what would happen in the UK. This is the target. This is what we've actually done. We're way below the target, but that's the easy lifting, get rid of coal. I can simulate a trajectory out to 2050 for the original 2050 plan in the Climate Change Act. And, sorry, I didn't mean to do that. And that's what it would look like. But to get down to net zero, which is now what the Climate Change Act hopes to get by 2050, you have to get rid of everything. No coal, no oil, no gas, no agriculture giving off emissions. You have to have agriculture that's emission-free, construction that's emission-free, waste that's emission-free, or find ways of sequestration and even extraction of CO2 from the atmosphere. Okay, I'm obviously beginning to run out of time, although I think James and Anne took a bit of time at the beginning to introduce the series, etc. So I'll quickly explain that we apply the same methods to modeling the costs of misforecasting hurricanes, which should be of considerable interest to any people listening in North America who lives anywhere near the coast in the southern US. They're the most costly weather and climate disasters: Katrina, Hurricane Maria, Sandy, Irma, Andrew. Climate change will alter the location, frequency, and intensity of such storms. It does forecast uncertainty, which is of interest to economists, impact hurricane damages. And my ex-student Andrew Martinez, now at the Treasury, shows yes, it does. So Andrew gets all the relevant variables: the incomes, the population, the housing units, the historical frequency of hurricanes, wind speed and pressure, max storm surge, max rainfall, hurricane cyclone energy, the existing conditions, soil, moisture, current air temperature, and adds in forecast uncertainty, plus 35 additional variables that don't matter. He applies autometrics, and guess what? It picks a few of them: income, housing units, minimum pressure, maximum storm surge, maximum rainfall, forecast uncertainty, which really does impact the costs that you get from hurricanes. Andrew has a website which shows that you can, say we take Harvey in 2017, there's an official damage estimate, there's various methods of forecasting that. This is the one that's like the AR1 that I showed you from volcanoes. This is the one that's like our shift from volcanoes and very, very close to official damages, and that's the 95% confidence interval. And this is how bad a simple model would be. And then he accumulates how much the savings are, and they're massive compared to the costs of having to fund federal agencies to do hurricane research and warn people of impending hurricanes. What's going to happen in future? Well, we want to get to 1.5 at most, rather than 2. And this was a submission by my group to IPCC report. That's 1.5. There are some bad cases, but just the extra ½ degree causes a massive increase, and another half beyond that will do likewise. This is ocean sea level rise. North America is going to suffer because it happens from gravity and ocean currents to be very close to a not very good area for sea level rise. So New York and Boston beware. So what can we do? Right, we've got to worry about high wet bulb heat. It's dangerous to life. It's already occurring in some countries. More powerful cyclones, increased coastal and inland flooding, longer droughts, worse wildfires, overly acidic oceans. So what can be done? First, we can decarbonize electricity generation. We use the earth for thermal heat, we use the air for wind, we use the fire for solar plus nuclear, and we use water for hydro. Renewables can eliminate coal, oil, and natural gas from electricity generation. That was going to require a massive increase in renewables and a massive increase in storage for still cloudy periods, and to balance grid supply facing much greater variability. Consequently, in a submission to the UK's National Audit Office recently, Janie and I suggested that we back up renewable generation by safe, small modular nuclear reactors based on well-developed nuclear submarine engines. We've shown that climate policy can be effective. It's part about big reductions. There's much more to do. But local losses were not addressed and must be in future. And the technical issues that the government should fund research into our storage systems and small modular reactors, which could use transuranic waste, which is currently a big problem of disposal, and or thorium. Next, decarbonize ground transport. It's a bit harder than decarbonizing electricity, but it's possible with electric vehicles, fuel cells, and hydrogen drivetrains. To sustain 100% renewables, we propose researching modular graphene-based carbon nanotubes to act as electro supercapacitors for storing electricity and recharging batteries. So we kind of envisage putting a whole lot of these in a Faraday cage in a unit on top of the vehicle's roof, which will greatly increase the distances electric vehicles can travel, and yet facilitate rapid charging and discharging. And if viable, and that's why we need research to check that it is, it would offer sufficiently light electricity storage to advance developments in electric aircraft, of which there are already several flying. We need to ensure that vehicles with such a thing are plugged into an intelligent grid when they're not used, and that's easily achieved by charging a much higher price to recharge their batteries. If they're not plugged in, that'll get people doing it. You've seen this removing plastic bags in Britain 18 billion from 5p per plastic bag. So vehicle to grid could provide a low-cost investment for electric storage systems. And that's all you need to have it. So you need supercapacitors and batteries, and a lot of research is going on in that. Intelligent infrastructure, charging, discharging points, and probably faster charging, discharging, which would require more careful balancing of the electrical system. And what more can be done? Well, we can decarbonize households, construction, and industry. We can replace households' use of natural gas by green hydrogen, produced by methane pyrolysis and electrolysis, produced when other electricity demands are low, like in the middle of the night, and store as liquid hydrogen, which also requires energy to cool it. We can retrofit old buildings for improved insulation. We can install hybrid or direct heat pumps, air and ground, solar photovoltaics, and evacuated solar collectors and roofs, and really provide houses with a lot of heating one way or the other. And we need net zero new buildings. That requires lower GHG intense materials, possibly wood, possibly making concrete without giving off greenhouse gases. In turn, liquid hydrogen could supply a high heat source for industry, but will still need carbon capture and storage and CO2 extraction, plus convert CO2 to a useful fuel, which is a lot going on. So several areas to research: perovskite-based solar windows to generate electricity within houses, efficient CCS, and definitely lower greenhouse gas refrigerants than the ones we're currently using, and lower building materials. Our proposal is we fund this research by prizes. Prizes have been really successful historically, from the Rainhill trials, the longitude problem, and so on. And it's essential to reduce CO2 emissions from agriculture. Down to earth, we need a lower footprint. When we submitted an article to the FT, they changed footprint back to footprint, thinking it was a typo, but no, we mean footprint. We need to reduce methane by ruminant dietary changes from uric acid, Asparagopsis taxiformis. We need human dietary changes to eat less mammal meat and eat less CO2 producing. We need to mix artificial fertilizers with basalt dust. Now, everybody knows that the land around volcanoes is much higher fertility than other land, and that's because basalt dust is a wonderful fertilizer. So instead of wasting huge amounts of money and producing a lot of CO2 from artificial ones, we should just be adopting basalt dust. And already told you that the Deccan traps produce 300,000 cubic kilometers of basalt, and we're not short of this stuff. It also absorbs CO2 as rainfall, with carbon dioxide dissolved in it, lands in basalt. It forms a concrete which stores the CO2 pretty much permanently. We need to cut cropland and environmental damage for better crop production efficiency, vertical and underground farms, and we need to improve agricultural production, better seaweed farming, kelp, seagrass, and Asparagopsis, and offshore wind farms help in doing that. Right. Policy implications. We need an integrated greenhouse gas strategy in removal. I haven't seen one. We need to replace oil by renewables electricity, huge expansion, vast storage requirements, balanced supply and demand, hydrogen from surplus electricity, and so on. But one of the byproducts of methane pyrolysis is black carbon, which is used to make graphene, lowering the costs of carbon nanotubes. We should increase taxes on oil as fall. This is simply to maintain the price at the same level, and the taxes can be redistributed either directly to people or used in other ways. I think we need a border CO2 tax on imports. So countries like China that are pumping out CO2 would face a tax on all their exports, and a tax in all countries where deforestation has been shown to be increased by our satellite measurements, so that every company in those countries will battle against further deforestation, because they would be facing much higher taxes trying to sell their products abroad. We need research into net CO2 absorbers, and stranded assets will be a problem if legislation or improved standards impose lower CO2 emission targets, and financial markets have not yet adjusted. Thank you. So finished.
Wow. Thank you very much, Dave. That was an extraordinary presentation with an enormous amount of information in it. For those people who wrote in asking if it was possible to get hold of the slides, yes, they have kindly agreed that we can make those available. And when the presentation is posted on the IIEP website shortly, the slides will also be available. And I can very much understand why so many people would like to have them. James, please step in if at any point you would like to pose a question. I have several pages of questions and comments and will have to restrain myself. But I am going to start off with one that also draws on one of the ones that was in the Q&A. Please, anybody who has a question they would like to pose, please put it in the Q&A so that we can see it. David, it's really clear from the data you present that what we're seeing now is not from the usual natural causes that have caused significant climate and abrupt climate change in the past, that we're doing it at a pace and scale that has not happened in the geological record, and it's not natural. That the human activity is very much endogenous. Yet we're still seeing very little action of the kind that you laid out at the end of what is necessary. And that's really appalling, given that your modeling of the UK data makes it very dramatically clear that policy impact can be quite visible quite quickly. Policy really matters. So when you present these kinds of findings to policymakers or to the private sector, how do they respond? And how do we connect the work that you have done, this very sophisticated data analysis, to human decision-making, and how do we do that quickly?
Yes, indeed. Obviously, we've tried conveying this to a lot of agencies. It's been seen by the Treasury, it's been seen by the Select Committee of Parliament that looks at science and economics. We've done it for the National Audit Office. We've published it on VoxEU, we've published it in Economic Observatory, we've published it in the Conversations, and we've tried all sorts of methods of getting the information out there. Everybody disagrees with some part of it. And rather like discovering that the cigarette lighter in your car doesn't work, so you throw away the car, they throw away everything, rather than just saying, well, I disagree with this bit, but well, let's go for the others. Because of course, when you get a consortium of everyone disagreeing with a little bit, they all think, oh, it's all disagreeable, we won't do it. Now, the British Parliament was almost totally unanimous in introducing the Climate Change Act of 2008. I mean, really remarkable across the right wing, the left wing, and the centre. People who actually were involved in many of these areas, everybody knew we had to do it, and we did it. The current government committing to net zero by 2050 has really put its head above the parapet. It's not clear how it's going to do it. It's announced a massive expansion of renewables, going from 24 to 54 new gigabytes of renewable supply. But that won't deal with the problem, right? I mean, you're going to need massive, if everything's got to be electric, right? It's not just that you've got to increase what we've got at the moment to get rid of coal, oil, and natural gas from electricity generation. You've got to increase it enough to get rid of everything from households and vehicles, which is going to require a massive extension. And I don't think we've yet got a clue about having sufficient storage. Indeed, I don't think we have an integrated greenhouse strategy, greenhouse gas reduction strategy anywhere, hence we've been proposing one.
For those who are wishing, for those of us in the United States who are thinking, I wonder what the difference is between your parliament and our Congress, there's an interesting backstory there about certain parts of the business community in Great Britain who played a very substantial role in making it clear that there was going to be political support for some of the action that was taken. It was still not an easy political thing, but it was made rather easier in the UK than it has been in the United States. So quite dramatic difference, and something that people in the United States might want to think about, the very important role that the private sector plays in the policy environment.
Yes, indeed.
Dr. Kessler, let me bring you in on this conversation too, because you've been so deeply involved in the modeling. And for those of us who are not econometricians, I was a little taken aback to hear David talk about how all the statistical methods that I learned about in grad school are simply not relevant to this story. Could you give us a little bit deeper understanding of what this modeling is and what is different about it, and just help us think through what it is that you're actually doing?
Okay, so in economics, we think a lot about how to model human behavior, and we interact in so many different ways that shift and change the world. And one of the main aspects that we need to deal with in economics is dealing with this non-constancy. So given the role of human behavior in climate change, we find exactly the same issues arise. And so at Climate Econometrics, we've been thinking very carefully about how to model change in all its very many forms. And really, David gave an indication of change is really what matters in his talk. So we've spent a lot of time developing new techniques that are able to model change and therefore ensure empirical rigor, which is really essential if we want to make policy recommendations off the back of the models. So the methodology that David presented it's fairly complex. We're using methods that maybe a few years ago people would have thought were absolutely crazy. We routinely include many more variables in our model than observations that we have to estimate them. And we do that using state-of-the-art machine learning tools to really hone in on the things that actually matter. And the methods that we've developed to model shifts are quite fundamental to trying to address this non-constancy that we're faced with. And these methods aim to help us find things in the data without assuming full knowledge at the outset. So, for example, we can measure policy reactions empirically rather than imposing them. So although the mechanics of the empirical models may seem a bit dull to those interested in the policy, the techniques really do matter for our understanding of climate change. And if we're to understand the messy data that we use, we need to be able to filter that data and process it in a way that really helps us to interpret what causal mechanisms are driving the climate change. It's not sufficient to develop elegant theories. They need to be taken to the data and tested rigorously. And that's quite hard to do when nothing is constant in the model. And that's why the econometric developments that we've been working on and that underpin David's talk, we think are quite fundamental.
Thank you very much. That is quite helpful. Techniques that can handle more variables than observations are the kinds of things I was taught you couldn't do in statistics. So this is very, very useful to know about. Lots of questions are coming in now in the Q&A. I hope that we will be able to get through a fair number of them, but we do only have 15 minutes left. So my apologies to anyone I don't get to. So we already talked a little bit about the impact that these approaches have had on the policy conversations, and clearly it's not having nearly enough of an impact on the policy conversations. Is there research that's been done, and this is a question to both David and Jenny, is there research that's been done looking at the impacts of policy changes in other countries to date? Do we have that yet, or is this an area that we ought to start pushing for so we can really start to see what impacts the policy changes are having on the variables that we care about?
Yeah, there are studies, even for the US, on policies at the county level that are encouraging counties to have both solar and wind turbine support, because then actually most of them that have that have very little coal and oil for generating electricity. There's big studies in Europe, the impact of France's nuclear program, of Germany's big changes, which it abolished nuclear and suddenly had to get much more coal. So it's going the wrong way. But there are changes of these sorts. And the pandemic, interestingly, has led to a widespread adoption of methods of looking at sudden changes, because you get a sudden change that the pandemic hits, and then there's a lockdown. And the lockdown wasn't predictable a couple of months before, and that shift then changes things very radically, very quickly. So the idea of having to deal with changes like this is coming in much more widely across the economics community. Hence, I hope we'll see more studies of what's happening. The US is actually doing better than many people think in eliminating coal and cutting its CO2. It's been falling quite a lot. And its capital stock has also got about a 92% increase in the efficiency of usage from 1860, well, actually 1870 in the US, because you had the Civil War up till then.
Right. Lots of very complimentary comments about the wonderful presentation and fascinating talk. There's one specific question about your views on the Stern-Nordhaus debate on social time preference rate and how it might affect some of the policy recommendations you have. And boy, do I want to hear the answer to this one.
Oh, yes. I'm totally with Nick. In fact, my first article was suggesting that if you're in a car rushing down a mountain and you suddenly discover there are no brakes, you jump, because it will get faster and faster and you will die. Even if the mountain has got a road 100 miles long or 2 miles long, that's irrelevant. What matters is when you're facing a disaster, you act now. Discount rates are simply irrelevant. And I think Nordhaus is completely wrong to focus on that. And even Nick, having quite a low one, is still putting the emphasis the wrong way. I was part of the team that tried to train Nick's group, and I argued strongly that discount rates should be ruled out. It's not, we're in a situation of danger. Like on the Titanic, you don't say, well, if it stays afloat for another 5 minutes, I'll go and use the bar. That's not how people are thinking, right? If it's going to go wrong, you get off.
Right. So your argument is it's not even the Stern-Nordhaus debate about what kind of discount to use. We should not be using a discount rate for the future at all.
No, we should not. We should be looking at saving ourselves now before it gets too late to do anything. And the idea that, well, we'll invent new things a few years down the road, we have no idea what they'll be, is just crazy in my view. I mean, I'm sort of like the school strike kids. I mean, I think they're onto it. I don't think Extinction Rebellion's quite understood the problem, but they are focusing on the need to do something rapidly. And I showed you that graph, the amount of CO2 in the atmosphere is accelerating. It's not slowing down. We're really going to overrun our carbon budget very, very quickly, and then have to do a completely disorderly change in how we produce electricity, how we travel, how we live. And I don't want to see that. Whereas if we start adjusting now, right, the benefits are quite clear that we can get to a situation that we don't change our lifestyles dramatically, but we do get rid of coal, oil, and gas. And if I may make one more comment that many people don't know, in the late 19th century, we almost had a fully electric economy in the world, right? It's quite surprising, but with electric cars, with electric turbines, with photovoltaic cells, all of that was around in the end of the 19th century. And the thing that went wrong was the discovery of the internal combustion engine. And that then misled everything. Even electricity was being produced by hydro initially in Britain and the US. So we can get back to an all-electric world.
So, but this raises one of the questions that's just come in, which is, what are the debt and spending implications of the transition? You've talked very clearly about, you can see signals from that point us toward having responsibilities for rapid change. We also have an economy that's suffering from a massive debt overhang, and the last year has made things catastrophically worse. How do we put these two realms together?
Yeah, I mean, I'm with your new head of the Treasury that this is a great time to borrow, right? Interest rates are negative or zero. If you're ever going to borrow for 50 years or 100 years. Even Argentina has been able to borrow for 100 years despite the regularity with which it defaults in its debt. So we borrow for long time periods at very low interest rates and we invest in it. And now is the time we need to do that. And yes, pandemic has messed things up a bit. And I've tried to show you it hasn't actually reduced CO2 and other emissions terribly much. It has reduced nitrogen oxides, and mainly because of a reduction in car transport. But no, this is the right time to do it. And we are at the crux of where we have the tools to be doing it. We know about graphene, we know about batteries, we know about turbines, we know about solar cells, we know about perovskite. All these things are just coming together. In my view, we've got 30 years to do it, Anne, and only 30 years, by which point we haven't got it completely under control by then, we might be facing big parts of the world where people can't live. You're going to see mass migration. That's going to lead to disputes and possibly wars. When I sat in the government's foresight panels a decade ago, our main worry was nuclear war between evil states where they start to run out of food and water because of climate change, and they can't work because of the wet bulb heat. And therefore, they start to go into other people's territory and their big friends come in and that could be one of the sources of mass extinction in the modern world.
Striking statement. James, let me turn to you for any question or comment that you care to pose before I get to our last couple of questions from the audience.
Right. I recently went to a local DC think tank discussion of climate change, and the current, I would say, conservative point of view seems to be, yes, we now accept that carbon is rising and it's rising at a high rate. But what we really don't know is what that means for people, for lifestyle, and for what we should expect in our future. The forecasting error is so huge we can't say anything. I want you, as one of the leaders in forecasting, to respond to that, if you would kindly, for me.
Tobacco companies are famous for trying to muddy the water, say, oh, it's uncertain, oh, it's not clear, no, we don't really know, the science isn't sure, therefore we needn't do anything, killing millions of people from lung cancer. So I don't take that the uncertainties mean anything. We do know what's happening to CO2. We know how fast it's rising. We know how temperatures are changing. We can tell you what sea level rise will be through to 2100 with near certainty, right? And we can say that there will be a lot of the parts of the world that you would not want to see flooded, right? Bangladesh is a classic example of a low-lying country, a very large population that's highly reliant on agriculture. It could get flooded quite soon, and especially if we get bigger cyclones, more powerful cyclones that then whip up higher storm surges which go further inland, which then, now, they happen not to be terribly friendly with their immediate neighbours, but they have a big friend on the other side of one of their big neighbours. And it's quite worrying to see that happening. So it's the precautionary principle. You may not know the uncertainty. And in one of our recent letters in the FT, we talked about murky glasses are a lot better than being blindfolded if you're going to drive.
So many more questions than we are going to have time to get to because we're down to our last couple of minutes. There is one that I'll throw in from the audience, and then I'm going, or two, before we can wrap up. One is a question about climate taxes, carbon taxes and other taxes related to climate. As you know, there's an enormous discussion going on about many economists saying if we would just price things properly and if we just taxed everything that is bad, can't we just solve the problem? Which also, of course, raises distributional questions. I'd very much like to hear your view on using taxes and how they should be implemented and what role they have vis-a-vis this much larger agenda that you have spelled out. Whoops.
In Britain, the tax on gasoline is about 90% of the price. And it has not discouraged motoring in any way, shape, or form. And the attempt in France to raise the price of gasoline by a small amount led to the Gilets jaunes violence all over the place. It's not obvious that carbon taxes can be implemented. It may be if you implement them, and I think the European trading system to cut carbon usage by putting up the cost of permits to pollute, because they fall in companies, can be implemented. But when they fall in people, you will find uprisings against the attempts to do it. Now, Australia had a wonderful clean green energy program that was brought in by Julia Gillard. and it was thrown out by the next government because people, even though they got all the revenue from the tax on carbon back to the people, so their lifestyle wasn't altered, they weren't even paying the tax, it was falling on companies, they rejected it. So many of these economists haven't looked at the behavior of human beings. They've looked at little Homo economicus in their models, right? And Homo economicus doesn't exist anywhere. It may get close to it in the US, but everywhere else, it's not what's going on. And the fact that 5 pence, a trivial amount of money on a shopping bag, led to a 98% reduction in their use, right? Because people didn't have to pay it if they didn't have the bags. Now, you can't avoid some of these other carbon taxes, and that's the problem. They have to pay them, and that's going to lead to the trouble.
On behalf of all the social scientists who are not economists, I have to tell you, it warms our hearts to hear one of the world's leading economists say that economicus is not the model we should be using in exploring what our policy options are. I very much agree with you on that one. Final question, because we are running out of time, and this is to both David and Jenny for any concluding thoughts. We're in a new administration in the United States, which obviously is tremendously important for the world as a whole in dealing with climate issues. What are the 2 or 3 priorities you would recommend to this administration? Or if you want to think of it in a different sense, if the magic climate genie came and grant you one policy or one technology, what is the one that you would focus on? What do we actually do now? Thank you very much.
Yes, well, joining Paris acts as a good role model, right? It doesn't do anything directly, but it's important to have the US as a role model. Finding a way, I mean, I can't think of an individual policy that would achieve everything that they'd want to achieve, but finding a way of shutting down coal and compensating the people involved by putting new industries into their areas is really very, very important. I mean, it was completely ignored by Thatcher. She just hated the miners, and so killing mining towns. My brother was a teacher in a mining town for a decade or more. And some of the kids at his school were the 3rd generation in a family that had never worked. And that's the kind of inequality we've got to avoid by having something replace the mining in those areas. And that's then going to apply to oil, right? That's going to be eliminated, notwithstanding Exxon's stubborn attempts like the tobacco industry to keep it going. Shell and BP have realized the writing's on the wall. The trouble is, most of oil is owned by other nations, not by oil companies. And so I think border taxes, if I'm going to do anything, so we put the costs on other countries to force them to adjust.
Jenny, would you care to weigh in on this?
Thanks. Well, yes, I think we know what needs to be done. We have much of the technology in place to undertake that. Financing, somewhat difficult, but as David's shown with the UK example, it certainly can be done, and prices of renewables will be falling. So I think the one thing that if this magic genie came along, it was fairly challenging. I would say it needs global leadership. We need global coordination. We know what needs to be done, but it's not being implemented. And some global leadership, I think, to force countries to do so would be very useful.
Thank you. So I'm afraid we have come to the end of our time. I just want to close by saying that my wish for the magic climate genie would be to get every leader in both the public and private sectors to listen to and understand the work that you've been doing. This very powerful explanation of, yes, climate change happens. It has happened throughout the geological record. It happens in ways that wipe out huge numbers of species. We are clearly driving it now. This is not a natural phenomenon. We can see in the evidence and in the data, when properly analyzed, the implications not only of what we're doing, but of the policy interventions that we can make. If we could get that understanding into everyone's hands, I think we might get some of that global leadership that Dr. Castle is calling for. And with that, let me thank all of you and our participants and our audience for joining us for this very important presentation today. Thank you very much.